we'll move swiftly on to Kevin Buzzard, who I've forgotten his title, but it's Teaching Mathematicians to Use Computer Theorem Provers. So, Kevin, if you'd like to take it away, please.
Right, wonderful. Can you hear me?
Yes.
Wonderful. So this is about an ongoing experiment that I'm doing, basically, with my career and with my undergraduates. So it's about a very complex pieces of software called interactive theorem provers, and the use of one such prover by me at Imperial College in London. So I'm going to start off by showing you what an interactive theorem prover looks like, and then I'm going to talk about two related but different things. I'm going to spend a lot of time talking about teaching mathematicians how to use the system, and then I'm going to say much less about teaching mathematics using the system. So there's somehow two slightly different things. So what's an interactive theorem prover? Well, there's lots of them. They've been designed by computer scientists. There's sort of, well over 20 in existence, and they're mostly being used by computer scientists to do computer sciencey things. It's quite a difficult, it's sort of difficult to enter the area because most documentation, these are complicated computer programs. Most documentation is written for computer scientists. So here's some examples of some interactive theorem provers that have got some mathematics in. So Lean, Cock, Isabelle Hall, Hollight, MetaMath, and Mizar. These are examples of these programs. So you're aware that there are things like computer algebra systems like Wolfram Alpha or Sage or Mathematica or R or Python, but these are different, slightly more exotic things. So the best way to understand what an interactive theorem prover is to actually see one in action. So let me just give you a brief demo of Lean. This is an interactive theorem prover. So this was a question that came up in the previous talk. You've got three integers a, b, and c, and I needed an example, so I just stole an example from the previous talk. And you've got the hypothesis, this hypothesis HAB that a divides b, and the hypothesis HBC that b divides c, and we want to prove that a divides c. So we saw in the previous talk how one might try and get that concept into Slack into Stack or something like that. But here's what this would look like in Lean. So the idea is I'm going to write computer code, which is sort of complicated and difficult to understand in this box on the left here. And on the right, we'll see the state of Lean's brain. So right now, Lean's brain knows that a, b, and c are integers, that a divides b and that b divides c. And we've got to prove that a divides c. So I'm going to type code into the left here. So what does it mean for a to divide b? I mean, one way of saying what it means is that there exists an x such that b equals a times x, right? So in fact, I can change. So internally, that's how this thing is. Let me exists an x such that something at HAB. So Lean's brain just changed a little bit there. HAB used to say a divides b, but now it says something which is mathematically equivalent, but not exactly the same. Instead of saying a divides b, it says there exists an x such that b equals a times x. And so we know this x exists, so we want to get our hands on it, so we can get it. Case is HAB with xhx. And so now you see the brain has changed again. Now we have an integer x, and we have a hypothesis that b is a times x. And we can do just the same thing with HBC. HBC says that b divides c, so we should be able to get case is HBC with yhy. And now again, so now we have a hypothesis. Now we have HBC is gone, but we have an integer y, and we know that c is b times y. And of course, we can, like hx says that b is a times x, so we can sub in, right? Substitute. We'll sub in. And so now we know that c is a times x times y. And we're trying to prove that a divides c. And so we can, so that means we've got to prove that there exists some integer such that c is a times that integer. So we can, of course, just use x times y there. And so now we have a hypothesis that C is A times X times Y, and we're trying to prove that C is A times X times Y. But I don't know if Stack catches this, but there's an issue of associativity here, right? C is actually A times X in brackets times Y. And we have to prove that C equals A times X times Y, but the brackets are in a slightly different place. So this is, at the end of the day, Lean, because it's very pedantic, will point out that this isn't obviously true by definition. We just need to use associativity of multiplication, or we could just use a high-powered. This is a statement which is true in all rings, so we can use the ring tactic. So there you go. What I'm doing there is I'm making, in some sense, a real meal of a relatively simple question, but I'm stepping through it using essentially only the axioms of mathematics. And as I say, even pointing out that somehow what you write on paper, what a student would write on paper, the student is never going to spot that at some point you need associativity of multiplication, because we just write. You see, without the brackets, that says A times X in brackets times Y anyway. So there's how to make a relatively simple question very difficult, and that's called interactive theorem provers. So this year I'm teaching 3 courses at Imperial, and every single one of them has got Lean in it. And so I'll give an overview of what's happening in these 3 courses. I'll spend most of the time talking about my final year undergraduate course. But before I start, I'll state the fundamental theorem of interactive theorem provers, which was taught to me by Athena, Toma, and Paola Iannone. Paola's on the call here. And what they observed, Athena watched me using this in an introduction to proof course. And what they observed is that trying to get a student, if I'm trying to teach a student an introduction to university level mathematics, and at the same time I'm trying to teach them how to use an incredibly complicated piece of software, then this is somehow doomed to failure, right? You can't teach a student how to use a vastly complex computer program and simultaneously, I mean, in the previous talk, it was mentioned that syntax entry and the use of the stack system was sometimes a problem. This was a quote from the slide, but believe you me, getting students to figure out syntax entry in Lean is a much, much bigger problem because Lean is an extremely pedantic interactive theorem prover. So as I say, this is the fundamental theorem of interactive theorem provers, is that you can't just stick them into an introduction to university mathematics course and hope that the students will begin to understand better sort of the concept of what a formal mathematical proof is. And this was my original plan, right? It was about start using this software in an introduction to proof course and make all the students suddenly have this very clear idea, because you see what's happening. One of the things the software is giving you is a very clear idea of what the nature of a proof is, right? We have up here, we have the hypotheses, and here we have the goal. This is the first thing you teach them. This is a weird logic symbol. And above the logic symbol is the hypotheses, and to the right of the logic symbol is the goal. And as the proof goes on, the hypotheses might change and the goal might change. And you have a sort of this idea about what you know and what you want and how that can change over time. And I think that's something that we sort of implicitly try to teach the students. But what interactive theorem provers are very good at is explicitly showing that to the students, explicitly showing what the nature of a formal mathematical proof is. But as I say, the obstruction to just doing this naturally, just dropping the software in, is that it's incredibly difficult to learn how to use the software. And of course, in a typical introduction to university mathematics course, an introduction to proof course, you've got many students who are struggling with the material. And so if they're struggling with the material, then forcing them to learn a complex piece of software is, of course, a step in the wrong direction. So what can we do instead? This is a question I've been asking myself for the last few years. And one thing you can do is you can take a mathematician, perhaps not a first year, but maybe a final year mathematician, and just teach them how to use the software anyway. I mean, we teach them how to use Python. Why shouldn't we teach them how to use an interactive theorem prover? Because it's a lot more fun than Python, especially if you're a pure mathematician. It's sort of coding, but with the boring parts removed, because you never have to run your code. You never have to worry about whether it's efficient or not. So my current system for teaching mathematicians how to use the software, by mathematician I mean undergraduate mathematicians, we have an informal part, which is a club I run on Thursday evenings. If you're ever in London, do pop in. And as well as that, over the last a year or so ago, I managed to persuade Imperial to let me start teaching a formal course, a final year course for final year mathematicians, final year BSc and also MSc students. There's now a course called Formalizing Mathematics. So let me say something about that course. Last year it ran, but it was still sort of slightly hampered because of COVID. But this year it's running for the first time next term. There's going to be 30 in-person lectures. And there's going to be no exam. That's something else that Paola taught me, is that just because it's a pure mathematics course, there doesn't necessarily have to be an exam at the end. So I ran this past the board that sort of deals with Imperial's teaching and learning, the curriculum, and they really like the idea of no exam. So now I have to think of something to do instead of an exam. And so what do we do instead of an exam? We do 3 projects. A first one due 4 weeks after the term starts, and then 8 weeks, and then 12 weeks. We have 11-week terms at Imperial. And so the hand-in date for the last course is a week after the end of term. And they're increasingly more and more valuable. And there's also something else Paola taught me was orals. So the first project, I have an oral, which is just really an excuse for me to meet the students on the course. They have an oral where I grill them on the code to make sure they wrote it. The second project, they get into pairs and do oral exams for each other. Each one has to explain their code to another person. And for the third project, I just organized a little conference. We had a mini conference that went on. But everyone spoke for, they just had a 5-minute slot. Was it 5 minutes? I think it was about 5 minutes, where they had to give a summary of what they did to the rest of the class. And these were all worth nothing. But as I say, we were mostly online. So, the presentations were all online. We had an online Teams call. So what actually goes on in the course? Well, we spend the first 4 weeks formalizing first-year undergraduate mathematical material. So you see, now I don't have to teach them the mathematics. This is the key difference. I'm not teaching them the mathematics. They know it already. What I'm doing is I'm teaching them how to use the software to do mathematics that they know already. This is the way round the Iannone-Thomas theorem. And the quotes lectures is just me doing live lean coding. It's all done by example. They learn by example, and I teach them by example. There is course material which is distributed. There are course notes, but the lectures are me taking stuff they learned in the first year and just doing it again, going through proofs they've seen already, like example sheet questions or standard theorems from the undergraduate linear algebra or analysis courses. Just doing them all live and lean, and very slowly. Obviously, the thing I did at the beginning was done very quickly because we're pushed for time, but I do it very slowly. So by the end of week 4, they have to submit their first project. And the topic of the project that they submit is they have to formalize, and I don't tell them what they have to do. If I say formalize the proof of the Bolzano-Weierstrass theorem, then one of them does it and 5 of them copy. So they have to choose a random piece of mathematics which they learned in their first year, and they have to formalize it. And of course, if 2 people choose the same piece of mathematics, then their code is going to be looked at very, very carefully. But in practice, they all choose different pieces of mathematics. And their job is to write a few hundred lines of lean code, formalizing the results, and then also a small PDF explaining what they did, how they did it, what they found hard, and what they learned. And they wanted to know what the mark scheme was, so I just stole our MSc project mark scheme. Is 30 marks of presentation, 30 for content, and 40 for bonus. And I was very vague last year as to what those meant, because I didn't really know what they meant at all myself. But this year I have a much better understanding of what those things mean, and I'll be explaining it to them next year. So that's the first project. Second project, they have to formalize something they learned in their second year. And then the idea is by weeks 9 to 11, the idea is they're supposed to actually know how to learn the system. So they can use the system now so that they can feel more confident doing mathematics which they've only just recently learned, and perhaps learning more about the mathematics which they supposedly know already when they start teaching it the computer, and the computer starts raising objections that they hadn't spotted. Perhaps they'll learn more about the material in their other courses. And yeah, the end of week 12, they have to formalize a theorem that they've learned in another course at some point in that year. So you see the MSc students have to formalize some MSc level mathematics. So that's the idea. That's the idea of what's going on in this undergraduate course. And as I say, last year was the first time it ran. We had 22 students out of 250 odd. Nobody dropped out, which was nice. And the office hours would just come to my club, come to my club and ask me questions. And if I'm busy, then ask somebody else at my club questions. Because of course, there are first year undergraduates who are experts in the system, right? This is what, there are people that get interested very early on. And by the time they're third years, they're better than me, right? That's another glorious thing about this, is that there's not really the barrier. There's not really the sort of the student teacher barrier anymore. It gets to the point where the students teach me things about the system, which I find very exciting, really. And I have a private Discord server with like 1,000 undergraduates in it from various universities around the world. And sixth formers and PhD students. This is, if people ask me for an invitation, they get one. And all of the students register. This is not an official, like Discord is not something officially sanctioned by Imperial, but they all get invites to. All the students have Discord. Discord is just a big thing for people that age, I've noticed. So the students just show up on Discord and they ask questions there, like all hours of the day or night. So I don't have to answer them because there's several world experts just hanging around on my Discord. So some students sort of spend a long time to get the hang of it, whereas of course others have been doing Lean for 2 years already because they've been coming to my club. They're already world experts. So it's a very interesting mix of people. And I don't care about telling the students how to use this. I don't really care about giving the students a lot of help with their projects, because at the end of the day, I don't really care about the marks. What I really want to do is to teach them how to use the system. And so, as I say, the course runs again in January. So how are we doing for time? Great. So I've got 3 slides left. So very briefly, the 2 other things I'm doing. So this term I was also teaching a graduate course as part of the EPSRC Talk Course Centre that we have at Imperial. So this is Imperial and several other universities. So this was PhD students coming. And that was an 8-week course, 8 2-hour lectures. And the first 4 weeks, I just sort of whizzed through the undergraduate material very, very quickly because I wanted to do something interesting in the last 4 weeks. So in the last 4 weeks, I just formalized a bunch of. So this is the forefront of modern mathematical research in this area. It turns out that master's level algebraic geometry has never been taught to a computer before, and so I sort of started developing Lean's. This might end up being a publication, a research publication, not a teaching publication. I taught the computer master's level algebraic geometry, and and so this was a very informal course. There was no exam, and the last 4 lectures I just stuck them on YouTube, and I got one of my PhD students got quite into the idea of formalizing master's level algebraic geometry and wrote a bunch of code themselves. And so my last lecture was just going through their code, basically, instead of writing my own code. So that was quite nice. I didn't have to prepare the course. But then finally, what's the other course I'm teaching? I am actually involved in teaching Imperial's Introduction to Proof course. Still, they didn't forcibly remove me from this course, even though I was using interactive theorem provers in the course. And what's happening there is I use Lean as a completely optional component. So we're going through basic proofs like, composite of injective functions is injective, that sort of thing. But because of COVID, of course, we had to rethink that course in 2020. So the students already have access to 100 pages of lecture notes and also lots and lots of 10-minute videos of me and other people explaining all the material in the course in a quotes normal way, proving that the composite of injective functions is injective, just in the traditional way you'd see in a textbook. And so in the lectures, what I do is I just can't be bothered to write on the board the proof that composite of injective functions is injective. So I just fire up Lean on my laptop and I just run through the proof in Lean and I just talk them through it very carefully. You know, I go through it much more slowly than I showed you earlier. Like in every line of Lean code I write a translation into human understandable mathematics. So they see the human understandable mathematics and then they see the line of Lean code. And basically the reason I do this is just an advertisement for my club. And you know, I say I'm well aware that some of you just don't have a clue what's going on right here, and that's fine. Just ignore this bit. Just pretend that I copied out a relevant piece of the lecture notes and just go and read the lecture notes, right? Because it's no different. I can't. What is the point of me copying out the lecture notes? But if you like what you're seeing and you're kind of interested in what's going on, then, you know, come to my club. So that's the end of my talk. And I have no idea what I'm doing, why, you know, I have no idea how to analyze what I'm doing or whether it's actually helping the student. I do know that the students that got very interested in this at the beginning are now sort of reliably getting PhD offers. So the pipeline is good. But of course, I think the reason for this is that the students that are interested in what I'm doing are typically the smartest students is what's happening. So we can't really deduce much from that. So why am I doing it at all if I can't figure out what it's actually doing? And one reason is I've taught Introduction to University Math. I've taught undergraduate courses for 25 years, and I personally find it doing this new way a whole lot of fun. You know, at the end of the day, I'm just kind of a hedonist who wants to play computer games at work. So reason two is, of course, we do teach the students a programming language. We teach them Python. We now have 2 Python courses at Imperial, gone up from 1. And if you're an applied mathematician, Python's very useful. But if you're a pure mathematician, then Python might not actually be particularly useful to you at all. And so why don't we teach pure mathematicians Lean instead? Because it's still a programming language, and yet it has more applications to pure mathematics in some sense, because you can prove theorems. And then reason 3 is sort of looking at the long game. These systems are going to get more powerful. You know, people are using them to do AI, to try and get AIs to generate proofs automatically. And, you know, I do think that these systems are going to start playing more of a role in sort of, research level mathematics. And so I think one can argue that because these systems are going to get better, they might become more important to research level mathematics, we should really be teaching our undergraduates how to use them. And perhaps maybe it will be some of my students who go on to make the systems better or have ideas about how to use them for teaching better or whatever. So that's really the reasons I'm doing it. And that's the end of my talk. Thank you very much.
All right, thank you. I'll lead the applause there. Right, we do have some time for questions. You can stick with your hand, or I can pick a question from the chat.
I didn't look at the chat, sorry. So feel free to pick.
Yeah, so there's a question from Christian Lawson Perfect here. Says the course seems to be quite freewheeling as you try to discover what works and what doesn't.
Yeah.
Are you starting to see a way towards a more structured curriculum that involves Lean? Pick a theorem from your first year courses would be far too vague a prompt for some students, and I expect there to be problems when a student picks something. Sorry, I'll say that again.
Yes.
And I expect there'll be problems when a student picks something that doesn't match your expectations. Yeah. So how do you deal with that?
So most of this stuff was being run online last year. So we were doing a lot of online chatting, and I would just encourage students to approach me individually, or my club had just started running again. So one of the most common questions for the first year course was, which theorem shall I formalize? And I made it absolutely clear that was the one question that I was not going to answer. So I was really quite ruthless. But on the other hand, I said, if you come up with an idea, I will talk to you all day about the pros and cons of that particular idea. So really you have to, so, some people would say, I want to do something. And I would say, yeah, that's great, except, be warned, it will take you a long time. Here's what you should do first, and here's a couple of techniques, and now go ahead and try it. And if you get stuck, then ask me for. I was more than happy to help students individually. You're right. I'm a very unstructured person. This is somehow the main problem, and I quite like freewheeling chaos. I sort of revel in that chaos, and I think basically over time, I will sort of try and figure out how to do it. But I think I just didn't want to set a lot of the project-based courses at Imperial are like, here's a project, do this project. And that was the one thing I didn't want to do because they would just cheat, right? They would just copy other people. So forcing them to do individual things was somehow a way of making sure they couldn't cheat. And I think it had to be like that. Next year, I think when they say, what shall we do? I might say, if they're really pushing me, I might say, okay, well, like, here's 10 things that people did last year. Maybe I don't want to say that. I don't know. I can't answer that question because I'm too chaotic.
Too chaotic. Well, it does mean that it's going to be hard handing this over to someone else if you were to somebody else doing it. But presumably they would just come in and structure it. And you're not particularly bothered about that, I guess.
No, I mean, at the minute, I can't see myself handing it over to anyone else because I can't really, because there's no other members of staff who are sort of capable of teaching it. I mean, it's the students that are capable of teaching it. Some of the students understand it better than me. They'd be the ones who could teach it. So it's a sort of a weird. Listen, as far as I'm concerned, this is just like, we've got a course that teaches them Python. I've got a course that teaches them Lean. You know, why not, right? If you think about it that way, that's one way of justifying it. And the other ways of justifying it, I'm still kind of working on that.
Right. Okay. So that sounds great. Well, I think we've kind of run out of time. I do know Paola has a question, but I guess she can ask you at some other point. So I'm sorry about that, Paola.
Yeah, that's fine.
So I'd just like to thank both speakers once again, so we can all give some applause. You can do that via the reactions.